Excellent, excellent. You're getting the hang of it. That's wonderful. Of course, this is an endothermic reaction. In order to get from here to here, I put in energy here. And then this must have high energy. I started out at this energy. This is the propanol. In order to get to isopropanol, I have to put in energy here, and this will have more energy. So this will burn hotter, but I asked which one burns cooler. That's this one then, okay? So one more corner to navigate. Intellectual corner, though. So this is, of course, it burns to CO2 and water. All this is hydrocarbon, burns to CO2 and water. So if we use CO2 and water, this is the enthalpies of formation. You use this, and you put them together, you get propanol, and the propanol releases that energy. Now, in order to get to isopropanol, you need to put in some extra energy. Okay, that's the difference. But when you burn it, it makes CO2 and water and releases more energy. So this one would burn hotter, and this would burn colder. And with this was the right answer. Now, let's do another little experiment. And we have here some propanol. And now forget that isopropanol. We're just talking about propanol, not that you think about isopropanol. Different experiment. So we have propanol here. Karen had put in some propanol here, and now she puts a towel in there, a paper towel, and she will heat it up, the paper towel. Burn that paper towel, and now feel the heat. Oh. Yeah, oh, it must be a lot of heat there. Oh, it's very hot. Do you feel the heat? Oh, I barely can touch it. Oh, very hot, very hot. Don't do that at home. Okay, it will burn the towel. Okay, so what we do now, see there's CO2 and water and some carbon, of course, from the towel. Carbon smoke. So what we do now, we take a mixture of 50%, not 100% propanol, we take 50% propanol and 50% water. And watch what happens. Takes a little longer because there's water, and you can touch this here nicely. See that? Oh. And there it happens. Our towel did not burn. No, it did not burn. Now, why did it not burn? Because we had water and propanol. The propanol was burning, and the water was at room temperature. Now, the water picked up the heat and took the heat away from the towel, evaporated, and with this, the temperature remained relatively cool so that it could touch the flame, and it just burned off, and it did not damage the towel. Let's do this with something much more interesting. Let's see what I have here. Oh, that's a $20 bill, yeah? Let's do that. It's all for you. Here's my $20 bill. Do you understand? The propanol burned, gave off the heat, but there was the water. The water says, oh, I'm going to take that heat, and I'm going to heat up to steam, and with this I transport away the energy, and it burns, but it doesn't burn hot enough to destroy the $20 bill. So this is something for fraternity members especially. But don't set your house on fire, okay? All right? So now let's go back to reality. So we need to see, if you can put the light a little bit down, thank you. We need to find out how do we get these enthalpies of formation for each of the compounds that we want to have in our chemical reaction. So first of all, we say that the elements in their standard state have an enthalpy of 0. What's going on here? Have an enthalpy of 0. That means in the standard state as we stand here, oxygen O2, enthalpy of formation is 0. Nitrogen N2, enthalpy of formation is 0. Carbon solid, enthalpy of formation is 0. Or let's see, anything, or chlorine gas, enthalpy of formation is 0. Okay, chlorine gas is also Cl2, so that you have. So we say that. Now there are two possibilities now when we can form these compounds out of these standard state elements. You have carbon and oxygen. You take one carbon, two oxygen. This is 0. You make CO2. Okay, CO2. You take carbon and two oxygen. You put it in a calorimeter and measure the heat when it happens at a certain temperature and pressure. And with this you get a number. And that number is when it is, and it's not necessarily for carbon. The number is, for example, it is a positive number. Then the individual elements have to roll up enthalpy hill to make that compound. All right. And so that would be a positive number. You also can have the situation, and this would be with CO2, for example, where carbon and two oxygens form CO2, and this reaction, when it happens, has a negative enthalpy of formation at standard state. That is 1 atmosphere, or one, in carbon, for example, it would be 1 atmosphere of oxygen. So, no, what's going on here? Okay, so you have the elements are formed in their standard state, and they form the compound that you want to use for your reaction. That is, for example, reactant A, you have that number, reactant B, you have the number. So what you do now, you want to have the standard enthalpy change, so you have your reactants and your products. First of all, you look it up in the table. You make the enthalpy of formation at standard states. You look up, what is this for my reactants? And this would be the enthalpy of formation at standard states. It's in the delta H of formation, not. Delta HF, not, is the enthalpy of formation at standard state. That was the little 0 on top there. And with this, you have the sum of the enthalpies of formation gives you the enthalpy of your reaction product. Not your reactant, okay? So you have to, of course, consider a stoichiometric factor, and this you have to read the book a little bit about. And so now we have the reactants, but we also want the products, and we make the products here the same way. Now we know what the enthalpy of formation for the sum of the reactants is, and we can calculate the enthalpy of formation for the sum of the products. And the difference between products and reactants will give you the enthalpy of formation for the reaction. So if this is negative, you see negative, you mean there is an exothermic reaction, that heat will be on the right side, heat will be here, heat will be liberated. If that is positive, that means the difference between this and that is positive. That means you need to put in heat in your system here to go to the products. That's all there is. So you look up the numbers and add them up and subtract them from each other, and then you are home free. So let's see. There's also, I could go make this reactants, okay? Make the reactants, the enthalpy of formation of the reactants. Then I have the reaction go and make the product. And when I go the opposite way here now and add this together, then I'm again here at the final state. So I started out here, made the enthalpy of formation of the reactants, then I made the reaction, and then I went from the product backwards to the elements in their standard state. What would be the change in delta H? The change in delta H. If I do that, I go this way, and then this way. 0. That's a state function. I'm at the beginning state, and at the end state, I'm at the same state. So nothing changed. So I did a circular process, and I came to the same result. It's called Hess's law, and you can use this very well to calculate some unknowns in this cycle here, and we will get some examples of that. So the delta H of reaction, delta H not, a standard state, that's always this 1 atmosphere and 1 mole, is the sum of the enthalpies of formation, the difference of the enthalpies of formation of the products, that's this here, minus the sum of the enthalpies of formation of the reactants. Okay? And when you get this, as you say, you can have, here's the numbers. Here are the numbers. You see, the enthalpy of formation for hydrogen gas is 0. Okay, it's H2. That's how we defined it. For oxygen is 0. For carbon, it's in solid state. Carbon is 0. Aluminum is 0. Iron is 0. Nitrogen gas is 0. But however, if you want to make out the natural hydrogen gas, you want to make one hydrogen atomic gas, a monoatomic gas, you need to split that bond. You need to take it apart, and you need energy to do that. With this, the enthalpy of formation is 218 kilojoules per mole. And if you have oxygen, you use 249 kilojoules per mole. And if you have nitrogen, N2, and you split it into one nitrogen gas, you have 473 kilojoules per mole. You see something in there, in these numbers? That's a single bond, that's a double bond, and that's a triple bond. So you need much more energy to break this than a single bond here, okay? So if we make carbon, for example, to make carbon gas, you need a lot of energy, and the enthalpy of formation of carbon in the gaseous state is plus 717 kilojoules per mole. If you make, however, CO2, as I explained earlier, you take carbon and oxygen, and that's a 0, and you measure that reaction, you get a minus 394 kilojoules per mole. That's an exothermic reaction. Energy is released. When you mix carbon and oxygen, you get minus 394 kilojoules per mole. Water, liquid water, you get minus 286 kilojoules per mole, and gaseous water, as we say, that's steam, you get 242 kilojoules per mole. Negative, of course. These are all exothermic. You see the difference between those? What is the difference? 44 kilojoules per mole. You've seen that before. That's the energy of vaporization. That's the energy go from the liquid into the gaseous state. And this is, for example, alcohol. Ethanol is minus 278. This is glucose. Glucose has a tremendous amount of energy that it gives off. That's why I like these sugary drinks, they give you lots of energy. And iron oxide, Fe2O3, has minus 824. If you have aluminum oxide, the formation of aluminum and oxygen to aluminum oxide gives a tremendous amount of heat off. And the formation of iron and oxygen gives also quite some heat off, but not as much as aluminum oxide, so that's about half of it. You see that? So if you have, for example, iron solid, and you put this in oxygen, gaseous oxygen, you get Fe2O3. That's iron oxide. That's rust, okay? And the next time we're going to do an experiment where I put iron, metallic iron into liquid oxygen, and we accelerate that reaction. We do super fast rusting. But I'm asking you now a question, what is the delta H, the formation of Fe2O3? Is it minus 575 kilojoules per mole, minus 824 kilojoules per mole, or minus 1073 kilojoules per mole? I hope you all can read, all right? Good. All right, let's go for it. Maybe you can put that board up there, please. What's that reaction? What's the delta H for that reaction? We're going to start in a minute. So they're all exothermic, obviously. Yes. Good. Okay, this is nothing but the enthalpy of formation. The enthalpy of formation, iron is its standard state is 0, this is 0, and this is measured, it's tabulated. And with this, the enthalpy of formation it says right here, minus 824. There it is, okay? Now, which of the following will react with iron oxide to produce molten iron? Why don't you vote quickly? And is it carbon, iron itself, or aluminum? And then we do an experiment, and I will explain all this to you the next time. But don't go away. You will see a very nice experiment. If you could go, while you are voting, go over there, far away from here, the first 2 rows. I need to evacuate the first 2 rows. Please go over there, and you over there to the stairs, and take a clicker with you. That will not. Just make sure you click something, okay? You leave your stuff, you can leave it. It will only burn, that's all. Okay, let's move quickly. We gotta go. Gotta get started. Go all the way to the side over there, far to the side. 1 second. So let's see what the result is here. Yeah, that's to be expected. So we have a mixture. It's called the thermite mixture. It has aluminum and iron oxide, Fe2O3 and aluminum. It's a mixture. It's not going to explode. It's a mixture. And this mixture we're going to ignite now in this pot here. There's a little fuse in here, and the pot is open at the bottom. So watch what happens here. Once we do this, I want to watch very carefully. Don't be scared. Okay, Karen, let's go. Watch. It's not going to explode, hopefully. You see that? There is molten iron down there. Molten iron. It flowed out of the pot. It was iron oxide, and we had aluminum. The answer was, of course, aluminum. And I will explain to the next time. They use this to weld rails together, railroad rails. This kind of is still used. That's 3,000 degrees up this. Okay? I see you on Wednesday.